Okay, let's discuss the chain rule in section 12.5. And as we mentioned, we had similarities to page 115 chain rule in 2-space. Now we're going to do it in 3-space and multi-dimension space. So basically, remember that we're going to be u of x is going to be a different u of xy. So let's look at 3-space first. So u of xy is going to be a differentiable function in terms of x and y, but then x is also going to be a function of, I think the book was calling that capital F of R and S. It's going to be a function of R and S, and y is going to be a function of R and S as well. Okay, and then all the partials exist. In other words, the partial of x with respect to R exists, the partial of x with respect to S exists, the partial of y with respect to both of those exists as well, with respect to R and with respect to S. These all exist. So if we have this for the chain rule, then if I want the partial of u with respect to R, for example, remember u is not defined in terms of R, so what this is going to equal by the chain rule is the partial of u with respect to x times the partial of x with respect to R, which we can do both of those parts, and then plus the partial of u with respect to y, and then times partial of y with respect to R. So if you notice on both of these, these kind of cancel each other out. Partial u with respect to R, that's what we wanted there. Partial u with respect to R is what we wanted there. And these kind of go away. But we do have a plus sign in the middle. So we're going to add up each parts of these. So that's kind of what that looks like. I'm going to show kind of a different look to this. So if we have u as a function of x and y, then the way that we can get from one to the other, like if I want to go this way, that'd be the partial of u with respect to x. So I could consider going down this part of the tree, kind of make a tree diagram as partial of u with respect to x. If I go down this branch of the tree, it's the partial of u with respect to y. And then x in turn is defined in terms of R and S. Now, since there are more than one variables there, these are also, if I go down this branch, that's a partial derivative as well. So it's going to be the partial derivative of x with respect to R. If I go down this other side, that branch, this is the partial of x with respect to S. Okay, now I can do the same thing over here with the y. So R and S. So if I go down this branch, this is the partial of y with respect to R, and the other side of the branch is the partial of y with respect to S. Okay, now if I want, in this case, I want the partial of u with respect to R. So here's where the u is, here's where the r's are. Okay, so I want the partial of u with respect to R, so I can follow the branches that get me there. So the first leg, so to speak, is the partial of u with respect to x, followed by the partial of x with respect to R, and that's what we have right here. And then I also have branches that lead from u to R down here, so that'd be the partial of u with respect to y, and then I would have to go this way, partial of y with respect to R, and if you notice, that leg is given right there, and then we're going to add them together. So we can kind of use these tree diagrams to help us calculate what the formula is, and then of course we can use this to come up with the solution. So let's actually do one here. I'm going to clear annotations, and let's just look at something easy like number one in the back. So if I've got u equals x squared minus y squared, that's u is a function of x and y, and we have x is defined to be 3r minus s, and I'm just going to make a small curvy s so that it doesn't look like a 5, and then y equals r plus 2s. So this kind of fits the exact format that we had. We're use a function of x and y are functions of r and s. All are differentiable. They're all polynomials, which means any partial derivatives would exist as well. So we're good to go on this. And if I just want to calculate the partial of u with respect to r, then we know since u is not defined in terms of r, then we need to use a chain rule. So it's going to be the partial of u with respect to x first times partial of x with respect to r, and then do this for every variable that we have. So in this case, we just have two variables, x and y, so that's partial u with respect to y, partial of y with respect to r. And once again, you know, the key here is, you know, this is what we start with, the du, and this is what we finish with, the dr partial derivatives there. And of course, you know, these kind of like they cancel out, and that kind of like they cancel out. But anyway, this is the chain rule. So let's go ahead and calculate these. The partial of u with respect to x, let's do that first. So the partial of u with respect to x, what's this equal? Up here, taking the partial derivative of that with respect to x is simply 2x. Everything else is a constant. And then I'm going to take the partial of u with respect to y. When I do that, it is 2y, right? And then times what we get for the other one. So let's do the other ones here. Let's take the partial of x with respect to r. Okay, here's my x function. Everything else is a constant, so that would just be times 3. And then I would get, I have a plus sign in between, right? And then the partial of y with respect to, I'll use a different color here just because I can. Partial of y with respect to r is just going to be 1 here. So this ends up being, for my final answer, is going to be 6x plus 2y, and that is in terms of, excuse me, not, am I needing a minus here? Let's see. Yeah, I needed a minus because I didn't do this right. This is a minus sign here. So the partial of u with respect to y, hopefully you noticed that I was messing that up, is minus 2y. So it'd actually be 6x minus 2y there for this partial derivative. So I'll let you do the other one. I'll let you do the partial of u with respect to s on this one and make sure that you get that. Now the other thing that that they're asking us to do on this is they're saying go ahead and sub in and see if you get the same answer. Once again, our answer is 6x minus 2y. So let me see if I can erase pretty easily. Hopefully I can. And give myself some room so I don't have to rewrite the functions. All right, so anyway, it probably would have been easier to rewrite the functions, but you know what? You kind of figure out technology by using it, I guess. All right, so we got a bunch of dots in space anyway. That's where we are because we're in R3, so these are like different star constellations out there, which is nice. Oh, hey, there's Sagittarius. That's my sign. Good deal. All right. So anyway, coming back, let's get back where I can draw. So that was my solution, but let's go ahead and sub in now. I'm just going to go. So everywhere there's an x, I'm gonna plug in 3r minus s. So u, if I put it in terms of r and s, then is going to be 3r minus s quantity squared, and then minus, when I plug the y in, is going to be r plus 2s quantity squared. Okay, Well, this isn't hard. This is just algebra, but obviously if that was to the 200th power, I 100% do not want to do this. So just like back in chapter 1, the chain rule is a very effective way to handle something that could get very complicated very quickly. But in this case, we can actually handle this pretty easy. So let's go ahead and do it. Let's square it out. The foil becomes the fool. So that's going to be 9r squared, and then multiply those two and double it. So minus 3rs doubled is minus 6rs, and then plus s squared for the first thing. And then I'm going to subtract this whole quantity. So I'm going to put parentheses around this. And for squaring this out, that's r squared, and then 2rs doubled is plus 4rs, and then plus 4s squared. Now I'm going to go ahead and distribute the that minus sign through there and try and simplify this to see what u is in terms of r and s as a function. So 9r squared minus r squared is 8r squared. And then we've got minus 6rs minus 4rs is minus 10rs. I might as well get rid of what I'm using so far. And then I've got s plus s squared minus 4s squared is minus 3s squared. So this is u rewritten as a function of r and s instead of as a function of x and y. And then, of course, if I take the partial of u with respect to r here, let's just make sure that I get the same answer. The answer, this was a y over here, but anyway, so it should be 6x minus 2y. Well, let's find out. If I take the partial of u with respect to r, I'm going to get 16r minus 10r. Well, that, excuse me, 10s minus 10s. And then, of course, the derivative of that, that'd be a constant, which would be 0. So be 16r minus 10s. Now, that doesn't look the same at all, does it? Let me just double check on this. So then what would we have to do? We would have to go ahead and sub in, right? 16r minus 10s, and anyway, this is a correct answer, but it's in terms of r and s. So if I really wanted to sub and see if these are equivalent, the question is, are these equivalent to each other? What would I need to do? I would need to take this x value, it'd probably be easier to plug into this, and then I would need to take this y value, plug it in right there, and make sure that that's the same. So let's just do the minus 2y would be minus 2r, and then minus 2 times plus 2s is minus 4s. That'd be the purple part. And let's go back and do the red part. If I'm plugging in x there, 6 times all that, 6 times 3r is 18r, and then 6 times minus x is minus s is minus 6s. So minus 6x. So 18r minus 6x. Anyway, coming back, let's combine this. So 18r minus 2r is actually 16r, like I had before, and then minus 6s minus 4s is minus 10s that I had over here as well. So it is true that these are equivalent, but we don't necessarily have to verify that they're equivalent necessarily in this. But anyway, so this is two different ways to do it. Once again, I'm just going to throw a lot of caution to the wind. So yellow light means caution, so we'll use yellow. If I made that to the 200th power or 2000th power or something, even 20th power, doesn't matter. All of a sudden, to try and sub these things in here and, you know, multiply them out and try and figure that out by anything other than the chain rule becomes a very daunting task, and we don't want to do that. Okay, so let's continue our discussion. I'm going to go ahead and clear this off, try and get back to a normal color, somewhat normal anyway. Was go back in black. So anyway, you know, there's a couple different chain rules. What if I have a differentiable function in terms of x, y, and z? Okay, and all the partials exist, and let's say that let's just say that x is a function of r and s, just like before, and y is a function of r and s, and z is also a function of r and s. So E, F, G, H, maybe h of rs. Okay, so anyway, long story short, they're functions of r and s. So what would if I wanted the partial of u with respect to r, how would I come up with that? Well, I could use that tree diagram, right? So to kind of come up with this, or I could use the concept, but let's try it with the tree diagram first. So here I've got u, and I know that u gets split. It is a function of three variables, x, y, and z, and then x is split into two variables. X is a function of r and s, y is a function of r and s, and z is a function of r and s. Okay, so what do I want? I want the partial of u with respect to r. So where are all my r's? So I got to follow the branches that lead me down there. And remember, when we have more than one line coming down from a variable, it's going to be a partial derivative. I am going to give you an example where we only have one line coming down, hopefully, by the time I'm done. So with this being said, I'm just going to follow the branches. I'm going to use different colors here. But anyway, for following down the X branch, let's just use blue for this one. But anyway, this would be the partial of u with respect to x coming down this branch, and then to get to the r branch at the finish there, that's going to be the partial of x with respect to r. Okay, so hopefully that makes sense. And then these are two things that we're going to need. So that's going to be partial of u with respect to x times partial of x with respect to r. And then plus, and then I'm going to add all the pieces, right? So I'm going to add on the next piece, which let's use red for that one, for the y values. So coming from u to y, this is going to be the partial of u with respect to y. And then down from y to r, this is going to be the partial of y with respect to r. Okay, so these are the two things I need there. So this is going to be plus the partial of u with respect to y times partial of y with respect to r, which is what we wanted there. And then plus, we got one more piece here. So I'm going to use green for this. So for the z branch, the branch that flows through the z. But anyway, going from u to z, taking a partial derivative, that'd be the partial of u with respect to z. And then if I'm going from z to r, this would be the partial of z with respect to r. So doing that, this is going to be the partial of u with respect to z times the partial of z with respect to r. Now, if you notice on all of these, it's like, you know, those cancel out, and I've got my partial u with respect to r there. I've got my partial u with respect to r there. And I've got my partial of u with respect to r there. So that's the other way that you could do that, is just go ahead and you split up utilizing the chain rule for each of those variables. So I'm going to try that one more time. I'm just say, what if we want the partial of u with respect to s? And I'm not going to draw this tree diagram out. Is there a way that we can kind of think about that concept-wise on there? So once again, three variables. So really this is like, you know, I guess 4 space if we've got a function in terms of three variables. But if for the same function I wanted the partial of u with respect to s, where u is a function of x, y, and z, and x, y, and z are all functions of r and s, how could I do that? Well, I want partial of u for my start, and then I need it for each variable. So partial of u with respect to x times partial of x with respect to what I want to finish with, and that's S. So partial of S, and then I need to do it for each variable here. So plus partial of U with respect to X times, excuse me, not X, Y is this one. Should have changed colors. Anyway, times partial of Y with respect to S. Okay, once again, you know, these are the start and finish, and I need to do it for every single variable. So I've got one more partial of U plus the partial of U with respect to Z times the partial of Z with respect to the finish line is S. Okay, once again, we've got all these, and as you notice here, you know, it's like these are cancel each other out. We're adding them all up, but we're doing it for each of the three variables for what they're split into. Okay, so hopefully that makes sense, and we'll go from there on that. Let's see. So I'm going to clear this off. I don't know how much time I have for examples on the video because I only get about 5 minutes left. But you know, let's just do an example of this since I had that up there. Let's say that U is x squared plus y squared plus z squared, just something easy like this. Let's say that x equals r squared plus 2s. Let's say that y equals 3 minus f squared, and let's say that z equals r cubed plus 4s. Okay, and what I want here, by the way, these are all polynomials. These are all differentiable functions, which mean all partials will exist as well. But if I want the partial of u with respect to s, okay, I'm going to do it in each part. So the first thing I need is partial of u with respect to the first variable, x, and then partial of x with respect to r. So doing this underneath, partial of u with respect to x, here's u, that's just 2x, times partial of x with respect to r is 2r, right? Now notice we have x's and r's here, so what we can do is we could actually sub in and see, you know, sub in that x with this x, right? And then we get it in terms of r and s when we're done. But anyway, that's the first one, and then let's do the second one. I'm going to use red for this. So plus, now I'm going to need the partial of u with respect to y times the partial of y with respect to, excuse me, whoa. I wanted with respect, I got to go back, I got to back up. I wanted with respect to s. So this has to be with respect to s. So that would just be on this one, that'd be the derivative of 2s is partial of x with respect to s is just 2 because the r squared is a constant. So that's my fault. So it's just 2x times 2 or 4x. So we did not have that combination there where we had to sub in. But anyway, so s is the finish line. Whoops, go back. S is the finish line. So just make sure that ds is the last thing, which I didn't do that in the first one. So anyway, and du is the start. But anyway, partial of u with respect to y is, of course, 2y. That's from up here because I have a y squared term. Everything else is a constant. Times partial of y with respect to s would be minus 2s. Now remember, this is multiplication here, not subtraction. So I'm going to actually multiply those two together, and I'm going to get minus 4ys for this one. And then, of course, here I could rewrite that y as 3 minus s squared and plug that in. And then let's do one more, and then plus the last one, the last variable here, I'm going to have z be the green one. This is going to be partial of u with respect to s, so I've got partial of u to start, but with respect to z first, and then partial of z with respect to the finish line is s, partial with respect to s. So once again, we've got that match here. So partial of u with respect to z is up here. Partial of u with respect to z is 2z. Everything else is a constant, so that'd be 0 times the partial of z with respect to s. So the r cubed is like a constant, that'd be 0. It would just be times 4. So this one's pretty easy. That ends up being 8z here. So reality is the partial of u with respect to s is going to be 4x from this one. So that's 4x. And then minus 4ys plus 8z. And then, of course, if I wanted to plug this y in right here, it'd be 4x times, or excuse me, minus 4 times 3 minus s squared times s, and then plus 8z. Does that really help? Not necessarily. You can multiply this minus 4 through there. But then what we could also do is I could plug in r's and s's here. This one. Whoops, this is my warning bell. To get done, I could sub this z in. If I wanted everything in terms of r's and s's, I could plug in this one for the x and this one for the z. I'll let you do that, but long story short, these are all correct answers if we know the parameters of what those equations are standing for, etc. So anyway, this is the chain rule, and just real quick, I wanted to show you if I have, I got to get where I can write. If I have u as a function of x and y, but then, well, let me change this up. Let's let u be a function of r and s, and then r be just a function of x, and s be just a function of x. So these are just, r might be something like x squared plus 2, and this could be 3x minus 4, something like that. But anyway, r and s only are defined in terms of one variable, but u is defined in two variables. So if I wanted the partial of u with respect to x, if I want something like that, so we got to be, let's kind of draw that tree diagram here. So I've got because I changed up the variables here, but u is defined in terms of r and s, right? But then r is only defined in terms of x, and s is only defined in terms of x. So if I want the partial of u with respect to x, I have to follow the branches from the beginning to the finish lines. So I do have to follow these, but how does that go then? Well, let's go from u to r first. So because u is defined in two variables, taking the derivative here is a partial derivative, so it's the partial of u with respect to r, and coming over here, this is the partial of u with respect to s. However, when I drop down and go from r to x, there is only one thing. So like if I have r equals x squared plus 2, the derivative of r with respect to x is just 2x, right? And that is just a direct derivative. It is not a partial derivative. So this would just be dr dx, not written as a partial, okay? Because there's only one variable here. So we don't have parts, two different parts like we did above with the r and s. We only have one piece, one branch coming from that. Similarly over here, s is defined only in terms of x. So if I want the derivative of s with respect to x, that's just 3 here, right? But anyway, this is ds dx. And then I'm going to follow these down. So anyway, the partial of u with respect to x is going to, I'll use different colors here, I think, possibly. Let's see if I have them. We'll do orange. I'm going to follow these. So it's going to be the partial of u with respect to r times dr dx. So once again, this is not a partial here because there's only one variable it's defined in terms of. And then plus the second part, see what color I got left, green, I still have green. Partial of u with respect to s and then times partial of, not partial, this is a direct derivative, ds times ds dx. Okay, so but notice very similar that, hey, even though that's a partial d derivative and this is a regular derivative, they still kind of cancel out. So it's still kind of like the, du dx. So even though that's a regular dx there, u is not defined directly in terms of x, so we can't just use regular d's here. This has to be a partial derivative. Same thing here, those s's cancel out, and we have those. So there's some examples in there as well. Just, don't let that confuse you, but if you only have one branch coming down, it's just a derivative. It's not a partial derivative. Partial derivative is when you have more than one part on your branches, and to get from one to the other would be a partial derivative then on these. Okay, hopefully that makes sense. And let's go ahead and get those 12-5 exercises done as well. And the ones I want you to do are number 2, 8, 14, and 38. So, okay, good luck.